A somewhat more advanced topic is a cluster analysis, which is the ability to group cases based on similarities in scores on the variables in the dataset. And that's what we're going to do in this particular movie. We're going to start by using a data set in R called MT Cars, and that's for Motor Trend Cars. It's road test data from 1974. I'm going to load this data set in, and we'll look at the first 5 rows. And what we have is a series of variables: miles per gallon, cylinders, displacement, horsepower, drivetrain final ratio, weight, quarter second times. VS, I've not been able to figure out what that means. AM is automatic or manual transmission. Gear is the number of gears. And carb is the number of carburetor barrels. Now, I don't want to use all of these. I'm going to select a few of them. I'm going to drop out a couple. I'm going to drop out VS. I'm also going to drop out the drivetrain ratio and create a new data set called MT Cars. Again, the way I do this is by asking for MT Cars and then selecting all of the rows. That's how I get it, by having in my square brackets, I just have a blank and then the comma. That means all of the rows. And then in the C here, I have the columns that I want: 1 through 4, 6 through 7, 9 through 11. And I'll feed that into a new object, new data frame called MT Cars 1. That's got 9 variables. Let's look at the first 5 rows of that data set. Okay, miles per gallon, cylinders, displacement, horsepower, weight, quarter second, automatic or manual, gears, and carburetor barrels. Now, when conducting a cluster analysis, there are at least 3 major categories of cluster analyses. The first is to split the data, split the cases into a set number of clusters. So for instance, you know ahead of time that you want 3 or 5 or 6. The most common version of this is the k-means, where k is the number of groups, and so that's often referred to as a k-means cluster. The second kind is a hierarchical cluster. That's where everybody starts separate and then they gradually get combined into more and more groups. Or dividing, where you start with a single group and split. Now, that's actually just another variation on the hierarchical cluster. And a hierarchical is in fact what we're going to do in this particular analysis. Now, to do a hierarchical cluster, the first thing you need is what's called a distance matrix or a dissimilarity matrix. And that means based on all of the variables in the data set, miles per gallon, so on, you need to figure out how similar or how different each of the cars is from each of the cases. So what I'm going to do right now is just use R's built-in function dist. That's distance. Although in the cluster literature, it's usually called dissimilarity. I'm going to save it into an object called D. And there, I've got that over there. Now, if you want to see what's in D, it's this huge matrix. So we'll take a very quick look, but not dwell on it. Let me make this bigger. And you can see what it has is all the cars listed on the side, and it's a little bit like a correlation matrix. It really is big. And what it does is it says how similar each of the cars is to every other. So the Mazda RX-4 and the Mazda RX-4 wagon, 0.61. That means there's a very little distance between them because they're very similar to each other. On the other hand, the Mazda RX-4 and the Hornet Sportabout have an enormous distance, and you get the idea as we go through. I'm going to clear the console because that's so much stuff. Okay, the next step is to use the distance matrix as the basis of our clustering. We're going to use the function hclust for hierarchical cluster analysis. And I'm just going to tell it to use the distance matrix and send that into a new object just called C for clusters. If we want to see the clusters themselves, I just type in the name of that. And here we go. It actually just tells us that it did a complete cluster method using Euclidean distance as a way of measuring the distance between objects. And there were 32 objects altogether. Now, the best part about a cluster analysis is a dendrogram, which means branches in Greek. And so we're going to get a picture of the branches. So I'm going to just plot C. Again, this is R's generic XY plotting function, but because I'm feeding it clusters, it knows how to plot those. So let me run that one. And then we're going to make this one bigger here so you can see it. And what it does is at the very bottom, every car is listed separately, from the Maserati Bora down to the Mercedes 280C. Each one's listed separately, and then as we go on the height of the dendrogram, they start getting combined. Some of them combine very quickly. For instance, right there in the middle, the Mercedes 450 SE and the Mercedes 450 SL combine quickly because they are similar cars. Some of them take a lot longer to collapse, and the Maserati Bora just kind of stands all by itself until it combines with a much larger group. But this is a hierarchical cluster. It tells you how long it takes for each car to become relatively similar to the others in terms of distances. We're going to come back to the dendrogram in a minute. Now, one of the things is we want to know what group does each of the particular cases fall into. We need to either specify that there are a specific number of groups, how many groups we want them to be, or we specify the height in the dendrogram. Let me show you that again. You see, height there is on the side. So if we picked a height of 100, the Maserati Bora would still be over there by itself. But if we picked a height of 300, there would only be two different groups. I'm going to pick 3. 3 seems like a reasonable number with this one. And so I'm using the function CUTree, or you might say cluster tree or cut tree. And I need to tell it where the clusters are. They're in my object called C. And then K equals 3 tells how many groups I want. And then I'm saving it as an object called G3 for 3 groups. By the way, if I use, instead of K equals 3, if I use H equals 230, 230 is about right there. You can see that I cut 1, 2, 3 groups going across. Let's take a look at the results of that. And now you can see it's listing each of the cars and the cluster that it goes into when I split it into 3 clusters. So the Mazda RX-4 and the wagon each go into cluster 1. The Datsun 7210 goes into cluster 1. At the bottom, the Porsche 914-2 goes into 1. The Pontiac Firebird on the bottom left goes into 3. And there you have it. Now, if you want to, you can actually take a look at several different groups of clusters at once. I'm going to call this GM for groups multiple. Using the same function, cut tree or CU tree, and I'm splitting the same clusters. But now, instead of specifying a single value for K, I'm specifying a range 2, 3, 4, and 5. And I'm going to do it this way. I run that, and then we can look at it, and it displays it a little bit differently. It's an interesting one, because now what we have is each car, and we have listed at the top 2, 3, 4, 5 is how many clusters there are. And what's interesting is to see some of them change around. So the Mazda RX-4 is always in cluster 1, but the Hornet 4Drive switches from 1 to 2. The Hornet Sportabout switches from 2 to 3. Most of them switch around just once. Down here at the bottom, the Fiat 128 and the Honda Civic, they're both in cluster 1 until we have 5 clusters, then they move to cluster 4. The most interesting one here, by the way, is the second from the bottom. It's the Maserati Bora, which back in '74, this was Maserati's really extraordinary supercar. You'll see later, it had much more horsepower than the others. It was very fast. It was very dramatic for its time. And it's in a different cluster every single time. And you can take a look right over here. It sort of makes sense because what's going on, you see the Maserati Bora is there standing all by itself on the left. It seems to be very different from everything else in this data set, which is interesting because we have a Ferrari in here, we've got a Porsche in here, but the Maserati stands alone empirically. All right. Now, one of the really neat tricks is to draw boxes around the clusters in the dendrogram. We use the function rect.hclust, so rectangles for a hierarchical cluster. We feed it the actual cluster data that's in the object that I created called C. We're going to start by drawing boxes around the 2 cluster, so K equals 2. And I'm going to draw it in gray. So just take a look over the dendrogram on the right. You see there's nothing there. Let's zoom in. It's just the chart like that. Now I'm going to draw some gray boxes. Now they're very light gray, but if I zoom in, you can see them, that they split it into 2 big groups based on this initial division. So we have the group on the left that goes from the Maserati Bora down to the Pontiac Firebird, and we have the group on the right starts with the Hornet 4Drive and goes to the Mercedes 280C. It's just an easier way of seeing the split. I can also draw it for 3 groups. So now I'm doing K equals 3, and I'm going to use a different color. And that's a bit darker. And you can see what's happened is the group on the left is the same. The group on the right, however, it is now splitting it. So it goes to the Hornet through the AMC Javelin, and then the Honda Civic through the Mercedes. And so it split it down that way. And again, this is all based on similarity in the data that was included in the data set. And I guess I should make that as a general. This is not an absolute final answer in terms of how similar they are. It's how similar are they based on the variables that I provided to the model. If I had different variables, I would get different clusters. That's an important thing to consider. Let's draw boxes around 4 clusters. What's interesting here is the only thing that changed is now the Maserati Bora is in its own cluster. It's separate from everything else, but otherwise everything's the same as the last one. And then finally, if we want to do boxes around 5 different clusters, I can do that in dark red. And let's take a closer look at that. Now what's happened is that the cluster on the far right has split. Now the Civic, the Corolla, the Fiat 128, and the Fiat X19 are in their own little cluster. And then we start from the Ferrari Dino, Lotus Europa, and go through to the Mercedes 280C in the final cluster. And if you're familiar with these cars, I am, you can see that there are some important similarities within each of these clusters. Now let's take just a moment and do a k-means clustering because it allows us to do some other things. I'm going to use the function k-means. That's the R function. I'm going to tell it to use the mtcars1 dataset and to split it into 3 clusters. Now, this is going to be very similar to what we did with our blue group just above with the rectangles. But I'm going to feed into an object km. And then when I print out the object km, here's what I get. It's a lot of stuff. It's telling me that it's created 3 clusters, one with 11 cases, one with 4, and one with 17. And then it gives me the means of each cluster on each of these variables. This is important because these can be used to form what are called centroids. And a centroid is a center, but in multiple dimensions. And so each of these clusters has a centroid defined by a point on these 9 different variables. So it's a 9-dimensional center. And you can see on some of them, there's a really big difference. There's a big difference on miles per gallon. Group 1, cluster 1 has 16, group 2 has 13, and group 3 has 24. Big difference on cylinders. 1 and 2 are basically all 8-cylinder engines, but group 3 is 4 and 6-cylinder engines. Very big differences in displacement, huge differences in horsepower, big differences in weight, where the average for group 3 is 2,500 pounds, but the average for group 2 is 49, nearly 5,000. The differences in quarter second are not nearly that big. The automatic versus manual. Now that's a dichotomous variable, zeros and ones. And what it tells us is that all of the cases in group 2 are automatics. And we have 18% manuals in group 1. And we have 65% manuals in group 3. We have the number of gears and the number of carburetor barrels. Then what we have beneath is which of the groups each one of them falls into. Now, giving them different numbers, the numbers are ultimately arbitrary, but they're going to be very similar to what we had before. Then we have what's called a sum of squares by cluster. It's sort of similar to the analysis of variance where you're looking at between group differences versus within group differences. And then these are the various components that we can look at more closely. Cluster, centers, total sum of squares, and so on at the bottom. I'm going to get a graph based on the k-means cluster. And to do this, I need to load a package called cluster that's part of the built-in R set, but it does need to be loaded. So I'm going to load that. Then I'm going to run this rather long bit of code. I'm going to run what's called clusplot. I tell it the data frame. I tell it where the cluster data are, that it's in km. We're going to color each of these, and then you'll see this thing about shading that draws lines, and it can be a little overwhelming, so I don't usually do it. And then we can have lines connecting the centroids, and then we can label the cluster. So let me highlight this whole thing and run that by doing command return. And it's a very different kind of plot. Let's zoom in on this for a minute. What we have now are circles that define the 3 clusters. We have cluster 1 in red, which goes from the Maserati Bora, the Pantera is in there. It looks like the Duster and the Camaro Z28 are in there. We have cluster 3 in blue that has the Mercedes and the Mazda, the Lotus and the Porsche and the Ferrari. And then we have cluster 2 in pink, which has the Chrysler Imperial, the Cadillac Fleetwood, the Lincoln Continental, which all makes sense. Obviously, there's a problem with labels overlapping here. Unfortunately, that's a very hard thing to fix in R. If you're going to do presentation graphics here, you might actually want to have it not do the labels and then add them manually, which is a major pain. But there's not an easy solution to the fact that the labels are overlapping, at least not for cluster plots. So unfortunately, that's what we're dealing with right now. But you can also see there's a little bit of overlap between the clusters. Okay, I'm going to close this for a minute. And I'm going to turn the shading on just so you can see what that looks like. I'm going to run the command by doing Shift Command P. And see, now it's got this little lines through it. And truthfully, I just think it makes it enormously busy. So I'm going to undo that, take it back off, run that command again. I think it's a little better that way. In any case, that is our initial take on clusters. Now, we're going to, in the next movie, talk about principal components and factor analysis, which can also be a way of looking at the relationships between variables, but a way of thinking about clusters as well. That's where we'll turn to in the